back to we don't understand. Oh, okay.
So you have to pathology. They got the margins.
Not used to, but not used to hear it.
Yeah, so I don't see any changes. I don't really totally.
Well, that means nowhere. The skin infection when you cut it off. There's no infection.
Yeah. He was kind of cranky that day.
But he was young.
They always go for margins. I got mine cut off.
So it was my fault maybe that.
That's real big. Margins.
It wasn't really very good at communicating to me what she wanted. She said, I love this album. So I was listening to a different album. She loved the sound.
We ordered 30 see what's all about.
90%,
I'm amazed that it
That's why we're
No, it wasn't that guy.
I'm glad you were able to.
one of them was great technology.
well, not yet. So what now? Phantom pain.
Less dynamic.
Yeah, go ahead.
Go drive off.
Just going so fast you can't run it.
I'm glad you were able to get around.
No, she said walking. She was
Yeah.
it's like that's worse than a doctor. Really? It's a lot worse than a doctor.
What you know? It's
Okay, everybody, you had a chance to go get something to drink? Okay, because I'm going to go ahead and get started. It's about 7:30. This could go on for a little while. I could easily go 45 minutes to an hour. So if you need to get up and leave, go to the bathroom, you know, anything but heckle, it's fine with me. Should I go ahead and get started?
Yes, go ahead.
Okay. Well, first of all, I'd like to thank Jay. He kind of pulled a lot of this together, invited me to come give the, the first talk. I'm really excited, and I'm honored to be here, giving a presentation at this society meeting. This is going to be a little bit different than what most of you guys do. I heard a lot of M's here, musicians, mixing, mastering. Well, I do the fourth one. I do a lot of math. But I'm going to work really hard to keep you guys entertained. So let's move on. So first of all, I'm going to give you some definitions and talk about some typical procedures. Then I will go through some application areas of audio forensics. I do have some representative cases, most of which you may have heard of. But I want to get a little legal issue out of the way here first. Normally, with a case, we don't talk about them, or at least until they're concluded and have become public. And that is true for most of these. The cases that I actually worked on, I wrote and got written permission from the lawyers. So I can go ahead and talk about hopefully some really interesting things. So, definition of audio forensics. So really, this is a field of forensic science. And I want to point out that word science, because we work really hard to have a solid scientific basis for this. And in audio forensics, it's really all about sound recordings and information derived from sound recordings that may ultimately be used in a court of law or in an official capacity. So evidence could come from a criminal investigation, or maybe fraud or an accident, something that may wind up having to go to court. And a lot of the primary aspects include establishing authenticity, analyzing and enhancing audio. And you have to be very careful when you enhance that you don't remove information in forensics. And then a lot of interpreting and documenting everything that you've done. So some typical steps are a prosecutor or a defense attorney will gather up all the information and ask somebody like me, to do some analysis. So typically they'll hand out a police report, and so I usually get a crime scene description, timeline, description of physical evidence, maybe even a map of where things occurred or what was left behind, and eyewitness and earwitness accounts. So an expert will do some audio analysis to answer some very specific questions. They provide a report, okay, and those results have to be justified with a reasonable degree of scientific certainty. So again, I'm going to use a lot of this reasonable degree of scientific certainty throughout this. An expert will provide a daubered justification of the analysis tools. I'll talk about that in a minute. And the expert, in the end, may be subpoenaed for testimony in a court of law, and he'll be called an expert witness. So that daubered standard is a federal law, and that determines the admissibility of evidence and expert witness testimony. And I want to point out a couple of things. Whenever somebody uses a technique, it has to be generally accepted in the scientific community. It has to be subjected to peer review and publication. It has to be able to be tested. And we also need to get an error rate, that is an acceptable rate of error. And determining that can often take years in getting publications. So that is what I spent many, many years doing, is analyzing, getting error rates, and attempting to publish. So we'll talk quite a bit about that. And my work doing all of that actually qualified me as an expert witness. So I want to first of all talk a little bit about earwitness accounts. So how many of you have heard of eyewitness? I'm sure everybody has. So anybody heard of an earwitness? Okay, very good. At least some of you watch detective shows. So I actually gave a talk on this at the AES Forensics Conference last summer, entitled Physics and Psychoacoustics Related to Forensic Earwitness Accounts. So you guys really should have heard that one. That was a lot of fun to talk about. So what is an earwitness? Okay, an earwitness is someone that reports events based on what they have heard as opposed to what they've seen. Okay, humans are really good at recognizing sounds, but they are not good at relating them at a later time. They're not very consistent. So the problem with earwitness reports or that they're very subjective, okay? And they vary from person to person. They're relative, they're not based on any kind of standard measurements. And standard measurements are really important in forensics, and those accounts can vary over time. So, just out of interest, does anybody recognize what this is?
It's a fennec fox.
Fennec fox. I thought about a bat, but bats are kind of ugly, and this guy is really cute. Okay, so Earwitness accounts usually require analyzing the physics of sound. Okay, and there we have to analyze propagation and attenuation, and also diffraction and refraction. So most of you guys have probably heard these terms, but sound will really vary in how it propagates at night versus during the day, in wind, going around barriers, and we have to analyze all of that because it really does determine what people can hear. And the same thing with ear anatomy and psychoacoustics. So psychoacoustics is really our mental perception of acoustic stimuli. And we really need to understand that whole mechanism. So ear anatomy is very important to understand. And then how we perceive loudness, pitch, timbre, and reverberation. And all of these things affect what people hear and how they describe what they hear. So I will have a couple of examples. Here's 3 cases that I actually had to work on. I'm not going to go into any detail here. One case, someone said, "I'm sure I heard multiple gunshots on the other side of that grove of trees." And this was a huge grove of trees. And normally that would completely attenuate the sound, and no one could hear it. However, this was late at night, and sound bends. It does not do spherical spreading. It starts to, and then it all bends down. I've actually run these experiments, and sure enough, definitely they could have heard it. Another one was, I was in my open garage, and I heard 2 different guns being fired across the street. I'm going to talk about this one a little bit later, but I wound up having to prove that that was not a reliable witness, and I could prove it. Another one was, I heard automatic gunfire and shots coming from a car chase on that road over there. So that was another very interesting one, and I wound up learning more about micro Uzis than I ever wanted to know. So, okay, one of the most important areas of audio forensics is authentication. And probably a lot of you have seen, detective shows or something where they had to analyze an audio tape. And traditionally, there was always analog recordings. And there they had to analyze the record and erase tracks, looking for stop and start signatures and splices. Okay, now these are pictures out of a very famous paper that was written by Bruce Koenig back in 1990, and this is in the AES, okay, Bruce Koenig was the head of the FBI audio and video forensics unit for the FBI. And he is the guy that actually hired me at the very beginning as a consultant. The other area here is also digital recordings, and this is what we get most of the time anymore. And there's actually a lot of active research, analyzing headers for consistency. Then we get down to analyzing the content of the audio. And typically we look for changes in the background. So I've done a lot of work, doing, statistical change detection so that we can identify these little areas like that. And one of the hot topics in authentication is examining the power line frequencies. What's called electrical network frequency analysis. And I don't know if anyone's heard of that, but different substations, if you look at that 60 hertz power lines, it's not exactly 60 hertz. There's a lot of variations, and that is usually unique to a particular substation or a particular area. So people can analyze that and say, no, that was not recorded in this area, it was actually recorded over here. Or if someone, edits something and there will be little breaks. Okay, this is little tiny deviations from 60 hertz. So that's again, a really hot topic.
I got a question for you. Because that wouldn't be true with like field recorders that are running on.
No. This is all. So the only way that might be true is if you're maybe under a power line or close to a power line and you got some induction. But a lot of times that's from something that's plugged into the wall. So I do have a case that I want to talk about, and this is one that you've probably heard of before. Linda Tripp secretly recorded conversations with Monica Lewinsky regarding her relationship with President Clinton. Monica handed those tapes over to Ken Starr, and she testified under oath that those were the original tapes. Well, the FBI analyzed them and found out that some of them were duplicates and there was missing information that they could prove. So therefore, they proved that Linda Tripp perjured herself under oath. And the guy that did all that analysis was actually my sponsor. So, you know, I every once in a while I hear, you know, really interesting little stories like that. Okay, quality analysis. Well, quality in audio is really how close recorded sound matches the original source. So most of the recordings that we get from the field are really pretty bad. Okay, they've been distorted in various ways, and these can be typically channel effects. You know, we talked about propagation, you know, noise, there could be interference that all gets added in. And then recording system effects, okay, microphones, filters, electronics, those can all distort that audio. So how do we analyze that? Typically it takes, you know, a trained expert that can qualify and also quantify these various factors, like signal to noise ratio. Is everybody familiar with that? That's really just the level of noise relative to the signal level. And as the noise gets high, the signal to noise ratio gets low, and the audio quality, you know, gets very poor. Also, there's interference. I should have added the duration of usable information in there. And then high pass, low pass filtering, clipping and saturation, I have to deal with that a lot, and evidence of compression. So these things are kind of hard to, you know, to detect, and then to also be able to describe or to quantify. So we worked really hard, and we have some standard measures that we can use. So starting an audio investigation, I typically, you know, will log in an audio sample that somebody sends me. I'll check the number of channels in that audio file, and I can't tell you how many times I've known people that were analyzing an audio file and they just analyzed one channel and not two, because usually there's a lot of information if there's a second channel. Perform critical listening. So I will listen to that and very carefully assess what I hear. Listen to the background, listen for other sounds, you know, interfering sounds, and just how good and how clear the information, you know, the actual signal that I want to hear. And then I'll plot the data and kind of continue that assessment. So I got permission to use this particular audio clip, and this is a set of gunfire, and there's actually multiple gunshots going off, and I will play it for you. Let's see if I can play it. And I could play that to you many times, and I would challenge anybody to tell me how many shots there were, first of all, and how many, or which one was which, if there were multiple, you know, firearms being fired, and who fired which. In other words, be able to identify each one of them. That's almost impossible, especially with something that's clipped and saturated and lots of background interference. And I actually pulled out a couple of these shots and plotted them up close. These do not look like anything what a classic gunshot signal would look like. So this is almost impossible to identify, okay, just using audio, but hopefully I'll have time at the end to describe a new technique which I've developed where I was actually able to identify every single one of those and who did what. So we'll get into that. But normally you'd look at that and you'd say, can't touch it. And that's kind of where I came in with the FBI. They would say that, and I'd come in and say, well, actually we can do something. Okay, voice analysis. Okay, this is kind of a really fun area. Really, this deals with voice biometrics and automated speaker recognition. Now, that's different from speech recognition, like your Siri or your Alexa can recognize your sound. Well, sometimes they might even be able to recognize who you are. But that wasn't true a long time ago. So there's really two areas of voice recognition. Speaker verification, and that is how similar one sound is to another. In other words, are those the same speakers? And that is the usual forensic case that we want to run. The other area is speaker identification, and that is really picking the most similar voice out of a list or out of a lineup. So if you're doing it visually, you'd pick, okay, the guy that committed this crime looked like, one of these people out of 10. So they would do the same thing, with speech, okay? Which one of these sounds the closest? Well, that's not a very good forensic, mechanism. So we really like to do this speaker verification, and that allows us to set thresholds and run statistical analysis, and we'll talk about error rates again in a minute. Okay, so I want to go back to some history, and this is my own personal history and involvement. Before the year 2000, the FBI relied on critical listening and spectrographic voice prints. So I have two voice prints up here, and I actually use the FBI standard method of generating voice prints. And can anybody out there tell me either what's being said in these, or can they tell me if these are from the same people? Anybody tell me that? Okay, nobody can, and what that tells me is that nobody took Victor Zhu's class at MIT, because Victor would actually teach people to read, and they can actually figure out what is being said, and to some extent might be able to tell if that was the same people. But that takes a lot of very special training, and a lot of the FBI were trained in that. But really, the results were quite poor, okay? And then in about mid-1990s, two events occurred. One of them is Doug Reynolds, who's now at MIT Lincoln Labs, published a very famous thesis on robust automatic speaker recognition with Gaussian mixture models. And I don't expect anybody to know what Gaussian mixture models are, but this was really a revolution. And error rates shot up almost overnight from below 10% up into the upper 90s, depending on the audio quality. So that was a huge, huge event. And the other big one was summer of 1996, the Summer Olympics in Atlanta. I don't know if you guys remember, but somebody called in, made a 911 call, and it went like this: there's a bomb in Centennial Park. You have 30 minutes. Now, was that or was that not Richard Jewell? And that question dominated everything that the FBI audio unit did for the next 8 years. They poured so much money, they did a lot of research, and it was actually pretty good for me too. Because after that happened, this is a little personal story, I was up at the FBI Engineering Research Facility in Quantico, Virginia, and I was giving a lecture on gunshot detection and acoustics. And after that lecture, the head of the division and the chief scientist cornered me and started asking me all these questions about voice and speech processing. Well, thankfully, I had taken all the classes, the graduate classes in digital speech processing at Rice, and I was able to answer all the questions, put up all the equations on the board, and I got hired on the spot to be their chief voice consultant. So that was actually pretty neat. Then in the early 2000s, NIST, okay, the National Institute of Standards, started the yearly ASR competition on standardized data sets. And again, they're looking at trying to set error rates and give universities and identify what the problem areas were. So a little bit before that, my sponsor had done the very first forensic data set, or forensic voice data set collection. And what was important about that, and extremely unique, is he got a large number of people, and he asked them to do different speaking tasks. So they had to do text-dependent prescribed speech. They'd have to say the exact same thing that everybody else said. Then they were asked to read different passages. So it was text-independent, but it was reading. And then he also recorded them doing conversations, which is also text-independent. Okay? And at the same time, all of the voice were recorded simultaneously using 3 different recording devices. So, since I was their chief consultant, I was hired to collect get all that data, organize it, and then conduct a blind test of all the top universities and companies that had the best automatic speaker recognition programs. So I got to conduct the test, get all the results, analyze them, and we got all the results and wrote a paper that was published. This is a peer-reviewed paper back in 2001. And what was really important about that paper is it really set the foundations for all of the problems that affect forensic voice data. Okay? And in particular, this different recorders and different speaking styles, everybody did very poorly with. So, and that really set a lot of the research that has gone on since about 2000. Then in 2004, I got to design the very first cross-language data set. So what we did is we got Korean speakers, and we had them do all of these speaking tasks in Korean and in English. Then we got Arabic speakers doing them in Arabic and English, and then Spanish speakers doing Spanish and English. So I got to analyze all those results, and all of that was then documented in this paper, again, peer-reviewed paper in 2004. And again, it was the very first cross-language recognition study. And then in 2006, we analyzed tens of thousands of telephone conversations. And the point of that was to derive a relationship between performance and several of these quality measures, like SNR and duration. And those results were, again, documented in another peer-reviewed paper in 2006. And so here's a couple of results that came out of that study. This is with duration. And so this is a longer duration, about 16 seconds, moving down. I don't know if you guys can see it. 16, 14, 12, 10, 8, 6, 4. All of a sudden at 4 seconds of usable speech information, the performance starts to drop off. 2, it really drops off. 1, it really drops off. We're getting down to really low performance there. So again, we're quantifying the error rates. And the same thing kind of happens with signal-to-noise ratio. High signal-to-noise ratios, we get very good performance, and then it starts to drop off and it gets very poor down at low signal-to-noise ratios. So, very important information, and those are, yes?
What's the high percent on the duration? Is it like get up to 99?
This is getting very close to 100. Okay? And then, yeah, this is 100, 90, 80, 70, 50. I think it stops down there at 20.
99 point something.
Yeah, yeah. So this is actually using some pretty good stuff. This is, 2006. We had some pretty good, and these were good quality data. And then we would shorten them, or we'd add a lot of noise or interference. We'd measure the amount of distortion that is going in, and then we would assess the performance over tens of thousands of speech samples. Yes?
What if it's the same word, like just no, you know?
So this is all taken out of a large random sampling, and so there may have been a few things like that, but we would test one against maybe thousands of samples. So it was designed to be, a very large and comprehensive study. So we did use these in some actual forensic cases. Okay, well, first of all, I'll talk a little bit about tools, and I'm not going to bore you guys too much. Does everybody know what a spectrogram is? Does anybody not know what a spectrogram is? So I'll describe that in case people don't know. So I have a linear spectrogram over here where we have linear frequency in kilohertz. Probably can't read it. And then we have time down on the bottom. And the way I like to describe FFTs and spectrograms is it's a bank of bandpass filters running over time. So we actually get to look at the distribution of spectral energy as a function of time. Okay, so you look at this and it's kind of difficult to read, what is that information up there? So it turns out that if we run that through a different mapping, so it's no longer linear, but now it's based on a scale that is very similar to the basilar membrane in your cochlea, all of a sudden, look what you can get, okay? All of a sudden, the critical information is really pulled out. And this is really what you hear, okay? Okay, you don't hear things on a linear scale. Everybody, all you music guys, you always think in terms of octaves and 12th octaves and things like that. So that's kind of what this scale is. It is an octave, or similar to an octave-based scale. I'm not going to run you through all the mathematics, but here's kind of the filters that wind up getting used. But anyway, so if we can run things through those kinds of mappings, very similar to what I call a perceptual scale, based on a human perceptual scale, it also has the advantage of reducing the dimensionality. So when we do statistical analysis on it, we can do a much better job. High dimensions, really difficult. Low dimensions, much easier. And we can use a lot of these very powerful statistical techniques. I mentioned the Gaussian mixture model. That was one of the first ones that was really provided a breakthrough. The I-vector technique solved a lot of the forensic problems. And now the hot topic that everybody wants to talk about and use is AI deep learning. And so error rates are really dropping, okay? These are providing a lot of very powerful techniques and doing extremely well. Okay, so let's talk about a couple of cases in forensic voice analysis. Okay, the first one I want to talk about is the Mumbai attack, okay, in 2008. Okay, there were 10 Pakistani terrorists, and they staged a distributed but coordinated attack throughout the city of Mumbai, India. And a lot of people were killed, but during the whole attack, 9 of those terrorists were killed, and 1 of them was captured. Okay, but the way that they coordinated that, and there were a number of planners that were in the U.S. and in Pakistan, and they were communicating over cell phones and satellite phones. So after that attack was over, the FBI collected all these phone calls, and there were thousands of them. And what I was told is that it would have taken them months to analyze all of that and figure out who talked to who and who these planners were. And by that time, they probably would have been gone. So we had provided the FBI with some statistical analysis techniques which helped identify and then help link all of these phone conversations and the people that were speaking. And they wound up, being able to go from months down to a little over a week. And they had all of the planners identified. They were able to go in, make all the arrests, and it was really a huge coup. But being able to do that quickly before anybody could, get up and, go to a different country or something like that was extremely important. So we felt like that was a really great result that came out of some of our analysis techniques. Okay, yes?
Just a side note, does that mean that the FBI is constantly recording phone calls before things happen? Were they involved terrorists and stuff like that?
So I don't know,
Okay.
and in fact, if I did know, I couldn't tell you. Yeah.
I have to kill you.
I'm just being paranoid.
Yeah, so I'm not really sure. I know that overseas especially, some phone calls are monitored, some phone calls there may be recorded, I don't know. But somehow they did manage to get hold of these. Amongst all of these millions of phone calls, and they were able to very quickly analyze them and figure out who was talking to who, and be able to get court orders to arrest them. So now I want to move on. Let's move up to the year 2012, and imagine everybody's heard of Trayvon Martin and George Zimmerman. Anybody not heard of them? There for a while, the headlines on the paper, every time you listen to the news, that's what they were talking about. Well, so what happened there was this young black man, Trayvon Martin, was wearing a hoodie, and he was walking through an affluent neighborhood in Florida, and this self-appointed night watchman named George Zimmerman, approached him and kind of, I don't know exactly what happened, but Trayvon Martin ran off. George Zimmerman followed him, and he saw them. He was up, between some houses. George Zimmerman called 911 and left it running. He ran up and he confronted Trayvon Martin again. They got into a tussle, and the result was that Trayvon Martin was shot and killed. So there was a recording of all of that, and in particular, there were some screams and some yells, and the question is who was screaming and yelling? So both sides, the defense and the prosecution, hired people, listening experts, that would basically claim that George on one side was screaming and yelling, and Trayvon Martin was screaming and yelling. So a couple of guys, Dr. Nakasone of the FBI, who is my sponsor, and Professor Jim Wayman of San Jose State University, he runs their forensic institute there, and Professor Wayman had been my mentor about 35 years ago, so I know all of these guys really, really well. And so they took my results that I showed you on one of the previous slides, and they use that as quantifiable evidence that you cannot take just a second or less than a second's worth of data and make a reliable identification. So based on that, they threw out all of these so-called experts that were each one saying what their attorney asked them to say. Okay, that's not good science.
Was one of those Tom Owen?
Yes. Yeah. So anyway, I was actually really pleased that they wound up being able to use these results, in a trial. And I was also pleased that I didn't have to get up there and testify. So gunshot analysis. So this is really one of the areas that I've done a tremendous amount of work and have gotten a lot of recognition for. Prior to 1995, the FBI had collected a very large data set of gunshot recordings, and they'd used, about 9 different recorders to do this. And when they got all that data in, they had no idea what to do with it. So they started asking around, and they found out that a little group at Traycor Applied Sciences here in Austin were the experts at analyzing short duration acoustic signals like pops, clicks, bangs. It's all from our underwater acoustics work. So they invited us up and talked to us, and then they eventually hired us to analyze all of that data. So what we wound up doing is performing a tremendous number of cross correlations and plotting data, looking at it, and wound up writing a paper with them. And again, this is Bruce Koenig, the head of the division, my sponsor, and of course me. And this was again an AES paper back in 1998, and this is a very widely cited paper. And probably the most famous picture out of that paper is this set of plots. So I'd like you guys to look at that. Okay, there's 9 different plots. Can anybody tell me how many different guns were used to make these plots? Just one. Okay? And they were all recorded at the same location, all the recorders, and these 9 different recorders. So when I showed them this, okay, they couldn't believe it. Okay, I mean, they literally were going, oh man, what are we going to do? You know, this is terrible. Well, being a good scientist, I explained what they needed to do. So I got funded to do the mother of all gunshot data collection experiments. So this is back in 1998. And what we did was we had a lot of high quality recording equipment. We did cross-angle recordings at multiple distances. And let me explain this picture here. So we had a shooter right here in red, and he was shooting up in this direction at a target. And for cross-angle, we had microphones placed at 3 degrees, 30, 60, 90, 120, 180, 120, 160, and 180. That's not right.
150.
Yeah, I can't see. I can't add either. Yeah. So then we also did cross range at multiple firing angles. So we actually would set microphones at 3 degrees, along this 3 degree line at 1.5 meters, 3 meters, 6 meters, and 30 meters. And they'd fire and we'd record all this data. And we made a lot of ground truth measurements. We tried to do a very, very good scientific study. And there's one of the FBI firing specialists, you know, shooting, and you can see the microphones set up.
Might be able to use it for a sample.
So some of the variables that we looked at was different firearm types, makes and models, different barrel lengths, different ammunition types and weights. And here's about half of the firearms. So we had revolvers, semi-automatic pistols, rifles, military-style rifles. We had shotguns. We had a lot of different things. And within each, we had lots of different makes and models. And within that, we sometimes had different barrel lengths and different bullet types and weights. And we measured bullet speed, sound pressure levels, all that good stuff.
Wow.
And so here's some of the results that came out of our study. So in this particular case, we were shooting up this direction. We had the microphones placed out at 90 degrees at different distances. And as you'd expect, you get a ground reflection. And the closer in, you get the largest distance that the ground reflection has to travel. So this is the ground reflection, and here's the really close in microphone. The next one out, you see it moves in further, and out at 30 degrees, it actually starts to interfere with the muzzle blast. Okay, again, that's kind of important to know. The other thing that you can see is really close in, there's a lot of high frequency, and as we move out, it gets smoother and smoother. In addition to being more attenuated, the smoothing is due to molecular absorption. And one of the other things, well, let me kind of jump over to this one, okay? Because this is the same firearm, at a different time. So this would be also out at 90 degrees, and you can notice that there's this little thing out in front of the main muzzle blast. And no one had ever seen that before. Nobody knew what that was. Now this is a revolver, and as you see, it doesn't look like that up front, okay? Things look really different, and as you move around the angles, you know, who would think that this and this are from the same shot? So again, the FBI is going, oh, you know, what do we do? But what's really interesting is I was able to identify what this little thing out in front is. Okay, again, that's a revolver, and revolvers are really leaky. So all that high pressure actually has a pre-blast coming out of the chamber. Okay, and then a little bit later, you get the main muzzle blast when the bullet exits the muzzle. Okay, and we were able to definitely identify that by having different revolvers of the same type, make, model, but with different barrel lengths. And so this distance would change. And that wasn't necessarily true with some of the semi-automatic pistols and some of the rifles. But anyway, there's a lot of kind of unique features, okay, that now people say, oh, well, maybe we can identify a revolver versus a pistol. And in fact, one of the AES fellows duplicated my experiment, and he gave a paper only on that at the last AES forensics conference. So this is actually kind of a big deal in the forensic community. And I'm not going to play these sounds for you because they're just too short. And I can hear the difference if I have headphones on, but when you have a speaker with a lot of mass, you can't hear the difference. It's just these little snaps. That's all you hear. So sorry about that, but we'll move on. So what I wound up doing is, taking, some subset of these, different revolvers, pistols, rifles, shotgun, and doing cross correlations. Okay, we wanted to, again, try to quantify what you can do in terms of analyzing and comparing, different makes, models, and different microphone positions. And it turns out it's not very good. So if we just do a cross-weapon correlation, it really doesn't look very good unless you're comparing one against, the very same set of circumstances. So, until we get over here to the semi-automatic pistols, and then they all kind of correlate pretty well, but they're really the only ones. So again, kind of important information, but once you do cross-weapon and cross-range correlation, okay, you really want something to be up here in the 95 to 100 in the correlation coefficient, up in the deep red. And we don't have any. And then it gets worse as we do cross-angle correlation, and even worse when we do cross-angle and cross-range. So again, that is really important information to know, okay? And that result is one of the ones I used in one of these Earwitness when the guy said, oh, I know exactly, that's a 38. I know what a 38 sounds like. And I will say, you know what a 38 sounds like from one position. And I bet you don't know what it sounds like out in front. And if you do, you're pretty stupid. What are you doing out in front? So, but anyway, so these are very important results, and all of this is documented in this paper. And everybody that does any gunshot analysis and any forensics, this is the fundamental paper that everybody cites. So we did this back in the experiment back in 1998. Why did it take so long to publish? Okay, so it took a lot of effort to do all that. But as I told you, speech and that darn Olympics, in Centennial Park thing, everybody lost all interest in gunshots for about 8 years. So we finally got back to it, finally got that published, and this is a very important paper. So, and again, this is the Journal of the Acoustical Society of America, not the AES, but I'm attempting to change some of that. So what are some of the typical gunshot analysis techniques? And again, these are important, to satisfy the Dauber criteria. That, in fact, this this list actually we put together for a trial as part of the Daubert hearing. And so we talk about critical listening, doing waveform analysis, looking at peaks and envelope amplitudes and waveform correlations, and the spectrographic analysis, and I'm probably the only one that does warped FFTs, for gunshots. Echo analysis, looking at reflections off of buildings or various other solid objects. And multi-shot timing analysis, I'm going to talk about this coming up next. And then finally, unsynchronized recorder timing analysis. And I'm probably the only person really looking at this, and I've got some papers in the works. Okay, so let's talk about some cases. So one of the very first cases that I got to work on, by myself, was National Geographic contacted me, and they wanted some analysis done, from the 1981 Reagan assassination attempt. So Ronald Reagan was at a speaking engagement at the Washington Hilton, and he came out of this door right here. He had a vehicle waiting for him along the side of the road, and over here there was a line of spectators, okay? And CBS, ABC, and NBC were there filming the president, and also one of the spectators was John Hinckley Jr., who, as Reagan approached his car, he pulled out his revolver and started shooting. So there is a conspiracy going around that there were two shooters, okay? And that second shooter, they claimed, was the one that actually shot President Reagan. Okay, so what National Geographic wanted me to do is to analyze the audio recordings and find out how many shots were fired and whether they were fired from the same location. Okay, so I had to have an approach. Okay, what am I going to do? Because I'll show you in a minute that these are kind of nasty recordings, very difficult to, it just, how do you answer those questions? Okay, yes?
Is that a curved wall? Is that wall curved in
Right
the
here?
center? Yeah.
Well, yeah, it is. It's not a sharp angle.
Yeah.
Okay. So the other thing is there's a lot of reflections that can come off here. So all this is going to make this be really kind of a what I would call a poor quality audio. But I wanted to do my best, so I was going to analyze the gunshot-like events, okay, because there's other things in there, including those reflections. From CBS, ABC, and NBC, audio recordings. And what I did was I analyzed time differences, okay, from successive shots, okay, from the three recordings. And then I got to design an experiment, and they flew me out here. I took these pictures, and then I got to actually go out. Well, I'll show you that in a minute, that experiment. But first of all, let me show you what the CBS recording looked like. Okay, here's the audio signal I plotted, and you'll hear President Reagan. You hear some hand claps, Mr. President. Then you hear a bunch of shots, and then you hear some kind of little clicky sounds out here. And I'm going to play that for you, if I can get out here. Bring this up. So this is what I actually had to work with. So let me do that again. So who can tell me how many shots were fired there? Might have been 5. Pretty hard to tell. So if we go back to look at this, I actually was able to identify 6. And then there were some other things. And why you said that, okay, I had to listen as many times with my Quiet Comfort 3 headphones, and I was finally able to pick out 6, and I slowed it down. I played all the little audio tricks that I could think of, And I finally sort of identified these 6. I tried to clean it up, but there's so many reflections and things like that that it was actually kind of difficult. And so I wound up, doing these time differences. And so I thought that, well, maybe I can tell something from that, but I wasn't really sure. So we designed this experiment, and let me get back into that mode. So we went up to a farm in Maryland. We obtained the exact same type of revolver as a Rome 22 caliber 6-shot revolver, just like what John Hinckley used. And we had multiple people there. We set up this little recording area or shooting area. And we had a target over here, and we asked these multiple people to aim and fire, and trying to be accurate and hit the target and fire as fast as they could. Okay, it used up all 6 rounds. And so here's one of them. And what we found out is that the measured time difference between successive shots was anywhere from about 0.3 seconds to about 0.45. And typically they'd start out a little faster, and then they'd slow down as they went. And the other interesting thing is that they didn't just do 6, but they keep going afterwards, so that there'd be these click sounds that they'd hear. Okay, and I just really, listening to that, well, you think maybe you know what it is, but you really don't until you go design an experiment and you put people under this kind of a stressful condition and ask them to do things, and it turns out that they all did about the same thing. So that's what we figured that John Hinckley probably did. So we wound up using that, going back and looking at the results for the CBS, the ABC, and the NBC time differences. So if I look at the successive differences between the shot number 1 and shot number 2, they're all very similar. Wow. And shot number 3 to shot number 2, again, very similar. Shot 4 to 3, again, all very similar, just within milliseconds of difference. Okay, so that was a really amazing result. Okay, and then at the end, I found these what I call these unknowns, and they also were very, very similar, within just milliseconds apart. Okay, and so I figured that these were those little clicks, where he'd run out of bullets, but he's still, squeezing that trigger. So this is the result that I wound up. The other thing, let me go back a little bit. Okay, so I called this Conspiracy Busters, okay? And the reason why I called it that was, it was a conspiracy, but the film crew that came in and filmed me and filmed our little experiment was the same film crew that films Mythbusters. So they were fantastic. This is just the most fun I think I've ever had, going out with that crew and working with them. So this was wound up writing a nice little report. As far as I know, they've never aired it. They had a whole series of these things. I don't know what happened, but anyway, I like to talk about it because it's a really cool result. And this actually has influenced a lot of my work that I've done since then. So let me talk about another case, and this is one that I actually had to be an expert witness. I got deposed. I actually got to take the stand, got cross-examined. It is not fun. Anyway, so let me describe the case a little bit. A young man led police on a 26-minute car chase around a major U.S. city. He was finally cornered at the entrance to a school by 13 officers. And in the end, in part of the police report, they found 137 expended shells, all Spear 99, okay, from a Glock, probably Glock 15s. And at the end, a police officer jumped on the hood of the car and he fired multiple times through the windshield, killing the driver. And no firearms were found inside the car. So, the question I was first asked is, can we tell with a high degree of scientific certainty if those 15 shots in the final barrage were fired by a single individual and from a single location. Okay, and I just have this one recording that was recorded from a police vehicle parked about a block away. So this is a really difficult case. I mean, how can you go through and make any kind of an accurate statement? So if you look at this, there's just a whole hodgepodge of things. And even when you look at this, it's really hard to pick out, and even count how many there are. So I did some kind of standard, FFT spectrogram analysis, looked at some little peaks, and nothing was showing off up. So then I decided to pull out some of my fancy techniques, and I used my cochlear model, and I did a third octave analysis and a spectrogram, and wow, just a huge difference. Now all of a sudden I can see, I can count all of these. I could find all of the interference. I could just remove it totally. And here's all the little peaks that come out of the envelope. And look at them over here. This is what everybody else, was showing. And here I come along and present this. And so I had to get this through the Daubert hearing because no one had done that. But we do this in speech all the time, just never applied it to gunshots. So this hopefully will also be in a paper coming out fairly soon. And I'll just play it for you just for fun, just that second barrage. Okay, so what's kind of interesting is I can hear it slow down. I can hear a regular pattern. Okay, when I look at the time plot there, I can't really pick it out, but my ear can pick out a lot of things. And I can pick this out, and that's because this is processing much more similar to the way our ear hears. So that's the way I like to do things. There's a lot of commonality. Uh-oh, I didn't mean to do that, sorry. Let you guys listen to it one more time. There. Okay, so the first thing I did was I go back to my timing analysis that I did for National Geographic. So I did time differences, and it turns out that they're all about the same, about, a third of a second, and they tend to slow down a little bit as it goes on. That was very consistent with what I'd found in all of these experiments that we did up in Maryland. So anyway, that's not necessarily provable, but that's actually, it's evidence, okay? And it's evidence that we can use. And the other question that I was then asked were the last shots in the first barrage, the middle shot, and the shots in the second barrage fired by a single individual from a single location. So then I had to do a little more investigation, play around with the math and see what I could come up with. So I wound up making a plot of cross-correlation coefficient versus peak amplitude. And what I found, and I cross-correlated them with one of the shots in that second barrage. And so this is the cross-correlation coefficient up in the 90%. So I got very good correlation, okay, of this set here in this little circle. And they all had very similar amplitudes. Then I did the same thing with the middle shot, and it was lower amplitude and also lower correlation. And then I also correlated against this set over here in the first, that should say first barrage. I made a mistake there. And they had also low correlation but higher amplitude. Okay, which means that this was probably fired closer to the recording device. So anyway, I could kind of answer that question that these are all very similar, and I actually kind of performed that with the rest of them, and it was a little more spread out, but it begins to look like it's there's a lot of evidence that says that those 15 shots were fired from one location. Okay, again, if he changed his position, if he'd even moved about that much, that it would not correlate as well. And if he'd moved to a different location and fired, they would not correlate as well. And that was a lot of the results in my big gunshot study that came out. So we wound up using a lot of that so that we could say that we felt like with a very high degree of scientific certainty that those 15 shots were fired by one person at one location. So that's what I was asked to do. So I have one more case I want to talk about, and I don't want to identify this one too much. I did get approval to talk about it at this level. So we had 3 shooters, okay, S1, S2, and S3, and we had 2 body mic recorders, okay, at this location and this location. And so S3 had his gun pointed up in the air, and S1 and S2 pointed their guns at S3 and told him to drop his firearm. And as he allegedly lowered the firearm, shooting started. And so they wanted to know who did what. And so the physical evidence, the 2 body microphone recordings, 4 .4 shells at S1 location, 4 of them at S2, and then 1 9mm at S3. So you'd think that there should be 3 shots that were recorded, okay? And what they want to know is what is the order of the shots, who did what, and well, who fired which shot, and why did they appear to change between the 2 recordings, okay? And these recorders are not synchronized. And sometimes one would be in front of another one, when you switch recorders. It was just a big mess. And you saw one of these before. This is my really poor audio recording. Okay, so here is the recording from receiver 1. And if I try and count these, I really only count 7 here, not 9. When I come down here, this is terrible. I can't really pick anything out. And over here on R2, I actually count 11. Okay? I was just kind of throwing up my hands, and everybody else did too. And I actually wrote a whole report just, quantifying the quality. This is such poor quality that we can't really tell anything. Then I went back to that work that I did for the National Geographic case, and I kind of identified some of these shots, but I wound up, kind of overlaying them and looking at them, and I remembered that things on multiple recorders that were, of a source at the same location are going to have the same time difference. So first of all, there was a little voice sample over here that was really evident in one of them, not in the other. You could see it if you did spectrogram, but that really told me that the speaker was really close to this particular recorder, and much further away here. And so I did my little timing analysis, and I found out that it was pretty close to the S1 shots. So I really think that the speaker, okay, let me go back over here. Was pretty close over here, and then I started doing these time differences, and I found out that E1, E3, E5, and E7, those are events, okay, all very consistent, all within hundredths of a second. The time differences. And then the same thing for the S2 shots. Okay, the voice was about 1/10 of a second difference as opposed to 100th of a second difference. And then, but these shots, 2, 4, 6, and 8, all very similar amongst the recorders. And the problem though was the last one. Okay, and it was very different. It didn't correspond to any of the others. So what I was able to say with I felt like a fairly high degree of certainty with the most terrible data, okay, is that that S3, that last shooter, was the last shot, and that contradicted what all the audio experts had said. So again, it's very difficult to to make those kinds of claims. But what I've done is I actually have the mathematics to back all of that up and to prove it. And that may be a paper that I publish very soon in the AES. So I'm trying to get a lot more active, and what we're trying to do is to apply a scientific basis for these kinds of analysis. So we have rigorous mathematics to back it up. So before I leave, I want to point out some forensic audio resources. There is an AES conference on audio forensics every 2 years. Last year they had one in Arlington, Virginia, and I was an invited speaker at that. That's where I gave my Earwitness talk. That was a lot of fun. The next one will be in Porto, Portugal. That will be a year from now. So if anybody's got some great things, want to go, it should be a lot of fun. And the other thing that I didn't know about really until about a year ago was the National Center for Media Forensics at the University of Colorado at Denver. And I've met a lot of those people now. They are a highly accredited program. And I know of a number of their graduates that have been hired by the FBI, so they're very highly regarded. So if anybody wants to go back to school, wants to go live in Denver, it actually is a really good program. So that's concludes my talk. I hope it was different.
Questions?
Yes, questions. Anybody have questions? Yes.
You had mentioned flexed FFTs on one of the slides, something
Well,
like
I
that.
say warped.
Warped.
Yes.
Would you describe that a little bit?
Okay, so normally when you take an FFT, you have a linear set of frequencies, okay, that you project your data down onto. So, if you might go 100 hertz, 200 hertz, 300 hertz, 400 hertz, and that is actually what enables the FFT is to have regularity, okay, the fast Fourier transform. Okay, so, but the way that our ear works is more on a logarithmic scale. And so if we take that FFT and we project it down onto a different scale, you can get something that appears to be more like your basilar membrane. Or the other way I actually, because I did a lot of work with the bionic ear, which is a cochlear implant, we actually had bandpass filters that we would space them, at logarithmic scales. And so that bionic ear actually, that was, I think, the very first cochlear implant that they surgically implanted in deaf people that had been able to hear, they'd gone deaf. And they were able to hear and understand speech. And so we were playing around with different number of filters and things like that. But anyway, so there's a lot of advantages in understanding, audio information, both visually and auditory, if you use a similar scale. Okay, and the other advantage is that it lowers the dimensionality, so you don't have so much to look at. So you can really pay attention to the same information that your brain is paying attention to when you're listening and trying to recognize sounds. So there's a lot of mappings, very standardized mappings that we use that we can project even an FFT down onto these warped scales. And they're typically described. Let me find, so Introduction to the Psychology of Hearing, they go through and talk about a lot of different scales that researchers have developed to model the basilar membrane. So, yes?
Okay, so when you get a case sent to you with a shooting and such, and you're listening to it, and you decide to rebuild or recreate the situation, and you're going to record it, capture it, and do tests like that, how important is it to use a recording device that's exactly the same as what was being used in the original situation?
So it's always better if you can do that, but a lot of times you can't. So I had another case, and I am not allowed to describe it to you, but they had a Sony camcorder with a Sony, gosh, I can't remember exact microphone, and I apologize because I spent a lot of time with people, but this was a stereo microphone, and I was able to pick out some really unusual things I could use to identify certain sounds versus other sounds from that stereo recording. I was actually doing a little bit of directionality work that I like to do a lot of that work too. So I had actually set up an experiment, and they were going to fund me to go up and actually use the exact same equipment and duplicate that experiment so that we could then prove that the analysis that I had done was accurate, and answered the question. I'm sorry I can't describe it. And then all of a sudden I guess there was just too much evidence, which included my evidence, and one of the lawyers decided, to not go forward with the case, and so I didn't get to do it. But that is actually what I recommend, if we can. But if you have a good quality microphone, a lot of times what I like to do is to get at the underlying physics and phenomenology that I'm trying to prove out. So it's good if I can get maybe a higher quality microphone, and then maybe something that is more similar if it's not as high quality.
Do you test a lot with like the body cams and built-in mics? Do you have a set of that you
No, I
use?
don't. And again, with one of these cases with body mics, I'd recommended that we go and we do some analysis and do testing, and they were gonna go get body mics, and then again that fell through, and I didn't get to do that. But yes, that is what I usually recommend when I'm doing a case that's really difficult. Yes. Any other questions? Yes.
Would you ever recommend to the police to get their audio synced up, something like that, so you have better?
So I don't know how you do that. Okay, because you've got guys kind of walking around, and I've tried to work this problem with distributed sensor nodes, and it's really kind of difficult. But there is a very small body of literature that talk about how do you do array processing and do localization with unsynchronized nodes. Okay, and it's a very small body, and that's the type of stuff that I'm trying to work with and trying to apply it to some of these cases. So there are conditions under which I can do it, but there's also things that I'll wind up with the big matrix, and I'll get millions of solutions, and I can't solve it yet. So I'm still working some of those issues, but there are things that I've discovered that I can do. And again, I've got a paper hopefully coming out pretty soon discussing a lot of those. An AES paper. So. Any other questions? Yes. I hadn't discussed that with anybody. I definitely could probably make at least a subset of them available. We'll talk about it.
Yeah, we can, if we have your email address, and Steve makes them available, we'll figure out a way to get them to you.
It's no pressure, I just curious.
Yeah.
Yeah, because we can just put it in a
I like it
Dropbox and
myself.
blast it out.
Yeah.
Super easy.
Yeah, that would be great.
Yes.
One of the slides you had technique getting the third harmonic. Was that?
I'm sorry?
In one of the slides you had a technique getting the third harmonics.
Yes.
Was that somewhere you filtering out the frequencies?
So was that third octave?
Third octave, sorry.
Right, yeah, so again, that's just a different mapping of the FFT spectrum, okay, and a lot of people that do outdoor noise measurements will do octave and third octave, filters. And so, again, that's a logarithmic scale, and that pulls out a lot of that same information. It's kind of similar to the way we hear, it's based on the basilar membrane scale. And if you do that, a lot of times you can see some interference. And so I was able to remove some of that interference that it just wasn't obvious in the FFT scale. So I removed that, and I actually got really much better peaks out when I looked at the envelope. I was able to count those, able to use that as my energy estimates. And then I could, make plots of that versus correlation coefficients and separate, these different groups of shootings. Yes?
Yes, do you use a digital or an analog FFT analyzer?
So I do both.
In both, okay.
Okay, so most of the time I'm on my computer and I
Yeah.
do digital FFT things, but I actually had my bionic ear. It's not mine. It's actually this professor I worked with up at MIT, and that is analog VLSI. Okay, so it's a little tiny little microchip with a whole bunch of analog filters on it that you can program, to set what center frequency that you want. And so I've done a lot of work with that. And then I have digital implementations of that. And actually I found that works better than if I try and warp an FFT down to that scale, if I actually use the bandpass filters. Those bandpass filters do a much better job. So I actually will run that, but I won't use that in a forensic setting because there's only very few people that understand what I'm actually doing there. So. Any other questions? Because I'm getting hoarse.
Cool. And that's it. Thank you.
Anybody
Thank
want
you.
to do well, thanks very much. I had a great time, and I hope everybody learned something tonight. So.
We have one more boring piece of information to get out. Steve has declined the vice chair role and instead nominated Tim. Can we just do a quick vote? All members that support Tim being vice chair, raise your hand. Anyone opposed? All right.